Okay, folks, in this PowerPoint presentation, we're going to talk about deriving quantum numbers and electron configuration. Note this layout. When energized, atoms of an individual element will give off light in specific wavelengths. Now, we've done this. A few months ago, this is a demonstration when we would take a gas discharge tube filled with a single element. We place it in a high voltage generator, and then we looked at it through our grating lens, right, which was basically small prisms, and we noticed that when it was an individual element we were looking at, we didn't see a continuous rainbow like looking at the sun. We saw lines of color, just as we do here in this illustration. Okay? For example, the line emission spectrum of hydrogen. This is distinct to hydrogen. You can in fact identify elements by their line spectrum. You've got purple about 420 nanometers. You've got blue about 440 nanometers. Green's about 480 nanometers. And about at 660 nanometers, you've got some red. Notice the examples here of the line spectra of a number of different elements: lithium, sodium, potassium, cadmium. These are like a fingerprint. You can identify an element by its line spectra. In fact, labs do this all the time in identifying unknown metals. Astronomers use line spectra to determine the elements in a star. They can actually break them out and determine not only which elements, but how much of each element is in that star. Okay, here's why we get line spectra. When an electron on an atom is excited, it will jump to a higher energy level. Now, it doesn't do this smoothly, it does it stepwise. And as you know, if you're climbing stairs, you can't just stop and stand in between the steps. You are actually taking those steps in quantum form. Quantum simply means stepwise. So when you have an excited electron, it will jump to a higher energy level and then almost immediately fall back down to a lower energy level. It releases the energy as it falls, and that energy is emitted as a packet of energy called a quanta. This is awesome in the form, almost exclusively in the form of photons. Okay? You can actually calculate the amount of energy being emitted by an electron moving from a higher to lower energy level. Energy equals Planck's constant times the frequency of the energy being released, the photon being released. Electrons that are not energized are said to be in ground state. Knowing how to determine the electron configuration allows you to give an address to every ground state electron on an atom. Every electron on an atom has 4 unique quantum numbers. The principal quantum number, designated N, angular momentum quantum number, L, magnetic quantum number, M sub L, and the magnetic spin quantum number, M sub S. And we're going to talk about how to derive these quantum numbers. The principal quantum number indicates the shell that an electron is in. A shell can have multiple subshells. The angular momentum quantum number indicates the subshell the electron is in, and the subshell can have multiple orbits. For example, look at the 3 spheres, 1s, 2s, 3s. In this example, the 1, the 2, and the 3 indicates the shell. The S indicates the subshell. There's only, in this case, one subshell to the shell. Moving up a level to the p orbitals, you have 3 subshells. I'm sorry, 3 orbitals per subshell. Okay? We'll talk in a moment what these S and Ps are anyway. The d orbital has 5. See, there is a pair of electrons in each one of these orbitals. So the 2d subshell can contain 2, 4, 6, 8, 10 electrons in total. Now think of these forms not as a distinct form. They're not balloons. Think of them more as clouds. They're fuzzy clouds that just happen to align in these shapes. Okay? Now, the principal quantum number, n, you simply number 1, 2, 3, 4, up to 7. The angular momentum quantum numbers, L, are derived from the principal quantum number. I'll show you how. Here's what you do. For the angular momentum quantum number, take the principal quantum number n and take all the values 0 to n minus 1. So for example, if your principal quantum number is 4, so n equals 4, all the possible angular momentum quantum numbers are going to be 0, 1, 2, and 3. See, it's all values. The angular momentum is all values beginning at 0 and then whole numbers up to 1 minus n, your principal quantum number. And just to make matters worse, you represent your angular momentum quantum numbers with letters. 0 is S, 1 is P, 2 is D, 3 is F. Now we go alphabetically. 4 is G, 5 is H, etc. The magnetic quantum number determines all possible orbitals in the subshell. M sub L equals all values negative L to positive L. For example, let's determine the magnetic quantum number, M sub L, if the angular momentum number is 4. The magnetic quantum numbers will be negative 4, negative 3, negative 2, negative 1, 0, 1, 2, 3, 4. The fourth quantum number, magnetic spin, it's actually easy. The magnetic spin quantum number is either going to be plus 1/2 or negative 1/2. That's it. Here is why. Electrons exist in an orbital as pairs. They can exist in an orbital as pairs. Now, initially you think this doesn't make sense because electrons are negative, so they want to repel. But if you have a charged particle and it is spinning, it will create a magnetic field. Two electrons will tolerate one another in the same orbital if they have opposite spins. Therefore, their magnetic fields will be opposite. That's why your only choices for the magnetic spin quantum number is plus 1/2 or minus 1/2. Again, a bit of the Schrodinger wave equation, which is rather advanced chemistry. We won't go into it here, but it does illustrate how the fourth quantum number, even though both these electrons would have the same charge, if they're spinning in opposite directions, they will have opposite polarities. Perhaps is a good way to put it. Okay? And there's your only two choices. It's a neat little experiment where you have an oven emitting electrons, go through a slit screen, and the spins of the electrons will show different results going through the magnetic field of the magnets due to their spin. Let's do some examples. Let's derive all the possible quantum numbers for the principal quantum number 1. So n equals 1. Now, all angular momentum quantum numbers are 0 to n minus 1. Well, if n is 1, 1 minus 1 is 0. The only value you have for your angular momentum quantum number is 0. And it's labeled S. Your magnetic quantum number, all values negative L to positive L. Well, the only angular momentum quantum number we have is 0. So negative 0, positive 0, all you can put is 0. And lastly, magnetic spin quantum number plus a half or minus a half. Let's do one a little more complicated. Let's derive all the possible quantum numbers for the principal quantum number 4. Principal quantum number n is 4. All values for the angular momentum quantum number are 0 to n minus 1. So 4 minus 1 is 3. So all your values are 0, 1, 2, and 3. And they are labeled S, P, D, F. Now, your magnetic quantum numbers. Take your angular momentum quantum numbers and write them negative to positive. So, your magnetic quantum numbers will be negative 3, negative 2, negative 1, 0, 1, 2, 3. And then your magnetic spin quantum numbers plus a half, minus a half. Now, using the 4 principal quantum numbers, we are going to develop an electron configuration table. Okay? We're going to work through principal quantum numbers 1, 2, 3, and 4. And we're going to go up to angular momentum numbers 0, 1, and 2. So, here's how it goes. 1. Principal quantum number 1. Angular momentum quantum number is always going to be 0. Magnetic quantum numbers, remember, negative to positive, but it's 0. So there's your 0. And then the magnetic spin quantum number is indicated by the direction of the arrow, which represents your electron. Okay? This is all about patterns. Notice the patterns, notice the patterns. Notice, regardless of the principal quantum number, if the angular momentum quantum number is S or 0, there is one orbital. S, one orbital. S, one orbital. S, one orbital. S, one orbital. If your angular momentum quantum number is P, always 3 orbitals. P, 1, 2, 3 orbitals. P, 1, 2, 3 orbitals. If we had 4p out here, it would have 3 orbitals. Let's look at D. Angular momentum quantum number 2, or D. We have one here in the example. D always has 5 orbitals. 1, 2, 3, 4, 5 orbitals. Now, these numbers to the right here, plus 2, plus 1, 0, negative 1, negative 2. These are your magnetic quantum numbers. Okay? Look at the example here. The arrow for the electron. The arrow pointing down, that's negative 1/2. Okay? The 4 quantum numbers for this electron are principal quantum number 3, angular momentum quantum number D2, magnetic quantum number -2, that's the orbital, -2. Magnetic spin is pointing downward, so let's say -1/2. So the 4 quantum numbers for the electron shown are 3, 2, -2, -1/2. Now, remember, the electrons are housed at different energy levels. The order of the energy levels goes like this. And if you have this little triangle, you can write an electron configuration table for any element you want. Here is the pattern. Remember, if you look straight across, that's your shell. There's the 1 shell, 2 shell, 3 shell, etc., 4 shell. Remember, the letter is your subshell. The angular momentum quantum number is the subshell, S, P, D. Your magnetic quantum number is the orbital number. That's not designated here, but if you will look, each of these energy levels has a superscript. The superscript tells you how many electrons you can have all together in that subshell. It tells you how many orbitals you can have. Remember, electrons can pair up, so you can put a maximum of 2 electrons in an orbital. So for example, 1s, you can put 2 electrons, that means it has 1 orbital. 2p, you can put 6 electrons, that means 3 orbitals. D, 10 electrons, 5 orbitals. Let's go back and look at our table. S, remember it was S2 on our triangle? You can put 2 electrons in this s orbital. 2 electrons in the 2s orbital. P had a maximum of 6. You have 3 orbitals. 2 electrons in each. 2, 4, 6. D. D had a superscript of 10. 2 electrons in each orbital. A total of 5 orbitals. 2, 4, 6, 8, 10. 1, 2, 3, 4, 5 orbitals. Okay? That's how it's done. You simply fill in the table, starting with the lowest energy level and moving to the right. As you fill in, when you're filling in a subshell like this, it's like moving college kids into the college campus. Put 1 student in each room of the dorm until there's a kid in every room, then come back and give them a roommate. Once that orbital is filled, the subshell's filled, move to the next subshell and fill it up. Okay? I hope you have found this helpful. Please do not hesitate to ask questions when you start working on the problems. Thanks.